Hi everybody, welcome to Related Rates. Look, it's a derivative, dy dx, right? We can say this as dy dx, but this thing, this derivative, which means slope, also has a much longer, wordier definition, and this is basically it. This is the rate of change of the variable y with respect to x. And so when we say dy dx, what we're sort of saying in a very short format is, hey, this is the rate of change of y with respect to x. It's telling us that y is a function of x, and that x and y are somehow related, and we can then find the slope and stuff between them. So that's what dy dx means in words. So what we're kind of going to do in this related rates video is no longer sort of think about y and x, but sort of think about like blue and red. Right? If we wanted to find the rate of change of blah thing in blue with respect to blah thing in red, right? The idea is that we're just going to do a derivative and somehow that'll magically make sense. Well, it's not magical. Like, I'm going to help explain it. So here we go. Problem. Find dy dt if y equals x cubed plus 3. Okay, this is weird. Because first of all, we're taking the derivative, notice, with respect to t. And there's no t in the problem. Interesting. Well, in a problem like this, it is assumed, you need to assume that both x and y are functions of t. And the way you will know if they're not functions, so let me finish, functions of t. Okay, the way you know that they're not functions of t is the problem will specifically say if the if the variables are constant. So if it says, oh, x is a constant, then you can treat it as constant. But if it doesn't explicitly say constant, then you need to treat it as a variable, treat it as a function of time. So what we're going to do is we're going to take this, and we're basically going to do implicit differentiation on it. So don't think too much about the t thing yet. The derivative of y is y prime. The derivative of x squared is 2x, and really, this is where that x prime comes in, okay? And then the derivative of 3 is 0, so plus 0, but really nothing, okay? And now, remember when we did implicit differentiation and differentiation up to this point, we said, oh, hey, x prime is 1 because it's dx dx. Very nice. But we have an issue here, and the issue is that we took the derivative with respect to t. And so in this case, because we took the derivative with respect to t, this x prime is really dx, wait for it, dt. And that's okay. Like, we want that. We want that dx dt there. And so our answer, right, this is the answer. But if we wanted to find dy dt, guess what? Y prime is the same as dy dt because t is the variable that we're taking the derivative with respect to. This 2x is just 2x, and we're just going to replace x prime with dx dt, and that would be our derivative for this problem. We'll see in a later example what we can actually do with this, but that's up to this point. So, looking at this, right, this thing is a rate, and this thing is also a rate, and the equal sign relates them. So we have like related rates. Sweet. Okay, going back to this. We mentioned earlier that there was a much wordier definition, like, because math is like all concise and nice and stuff. And so here's like the super wordy definition for this. Parentheses. The rate of change of y with respect to t, and t usually actually means time, so we can actually just fill it in with time, is equal to, okay, so here's how we're doing this. So the rate of change of y with respect to time is this thing, blue, the rate of change of y with respect to time. The equal sign is equal to, rather. And then, let's do this, 2 times x times, and that's this part, right? 2 times x times, that's there. And then the rate of change of x. with respect to time. And that would be this last thing. This dx dt is the rate of change of x with respect to time. End quote. You can quote me as saying that, Mr. DRAM. That was a terrible M. Let me try that again. All right, Mr. DRAM says that. Okay, for history class. Okay, anyway, so yeah, so math is much nicer because it's super concise and we just sort of write that, but this is what it means in words. Okay, so let's do like a real math problem that actually is kind of interesting. So here we go. Okay, here's a nice little problem. Find the rate of change of the area of a circle if the rate of change of its radius is 2 and its area is 36 pi. Or really, we could say when its area is 36 pi. So, things that you need are, first of all, an equation. Well, that's kind of fun. Hey, we're dealing with the area of a circle. We know that the equation for the area of a circle is a equals pi r squared. Okay, and because we're talking about here's a nice little word thing, right? The rate of change of the area, that's a thing, and that thing is a prime, right? It's the derivative of a, or we could say dA dt. Yeah, and then here, right? The rate of change of its radius is 2. That's dr dt or r prime, and that's going to equal 2. So eventually we're going to like plug that in somewhere. And then here we know that at some point the area is 36 pi, but we're not quite there yet, so let's hold off on that. Okay, so here's what we're going to do. We're going to take our equation, and because we have a and we need a prime, we're going to take the derivative. Derivative, woo! Okay, and so the derivative of a is a prime. Pi we know is a constant, so it stays there. And the derivative of r squared, right, it says nowhere does it say that r is a constant, so we're going to take the derivative using like implicit differentiation. So it's going to be 2r, and then chain rule r prime. Basically, whenever you have a variable, you're going to chain rule at the end, and you're going to get that variable primed at the end. So if you have like Optimus, and take the derivative, then you get Optimus prime. Okay, that was a bad joke. Okay, so we're almost done, because like now we just plug stuff in. So we're looking for a prime. We have pi. We have 2. We don't have r yet, so we'll get there. But we know that r prime, we have that over here. There's our puzzle piece, right? It's 2. Okay, and now we need to find the radius. Well, to find the radius, we know, look at this. Hey, look. It says that the area is 36 pi at this particular moment. And so because the area is 36 pi, we're going to say, okay, 36 equals pi r squared. And so, no, 36 pi equals pi r squared. So the pi's are going to cancel, and we get r as 6. So we can take 6 and plug it in. And so therefore, a prime is going to be 2 times 6 times 2, which is like 24 pi. And that would be our answer. Here's a visual process of what's happening. You're taking a circle, and the radius of the circle is increasing. So like at one moment it's this. The next moment, the radius has increased by 2 units. And in the next moment, the radius has increased by 2 units. And at some point, right, the radius gets to 6. And at that moment, that's when we are trying to find the rate of change of the area. So let's say we're at that place, and we have our circle, and its radius is 6, there, like that. And now, if we increase the radius by a tiny amount, really that's like that little blue thing, that's our r prime. It's our dr, it's our change in r, right? All of these things are approximately the same idea. And if we think about the new area that's just been added, it's so incredibly small. Oh, that was bad. Let's do this better. If we think about that new little thin ring that's just been added to the circle, well, that thin ring kind of goes all the way around the circle, and it's kind of like the circumference of the circle, and oh my gosh, look, it's 2 pi r coming from the derivative, right? The rate of change of the area is related to the radius by the circumference. That's kind of cool. But wait, let's say you had a sphere, and the sphere was 4/3 pi r cubed, because that's the volume. And you're like, hey, I got my sphere. Three-dimensional? Question mark? No, that was bad. And now we increase the radius by a slight amount, right? And we should get like we're adding like a little extra shell on the outside of our sphere. Well, that shell is kind of like the surface area of our sphere. Oh, so maybe if we take the derivative of this, we'll get something that should maybe relate to this. So watch. V, the derivative of V is V prime. And 4/3 pi is constant, so it stays there. And the derivative of r cubed is 3r squared, chain rule r prime. And check it out. This thing here simplifies because the 3's cancel. Oh my gosh, you get 4 pi r squared, which is the surface area of a sphere. Right? It's not by accident that we have these formulas. These formulas make sense because of related rates. Cool.